Bismillahirrahmanirrahim. I welcome you to the fifth lecture of the series of lectures on advanced computer architecture. Today, first of all, I will give you a small review of our previous lecture. Then our today's focus will be the discussion on instruction set encoding and MIPS instruction set format. Last time, in our fourth lecture, we started our discussion with describing the three basic pillars of computer architecture. These pillars are the hardware, software, and the instruction set architecture. Then we talked in details what is an instruction set and what is the taxonomy of the instruction set. That is, what are different categorizations? For example, what is a stack computer architecture, what is accumulator-based computer architecture, and what is a general purpose register-based architecture. Then we highlighted the types of data and the operands and how they can be specified, what are their sizes, and what are their types which are acceptable in computer system design and computer architecture. Then we discussed the classification of operations, that is the arithmetic operation, the logical operations, then data transfer operations and control operations. Then we discussed different addressing modes of the operand, that is how we can define an operand with an instruction, whether it can be defined in an immediate mode or in register addressing mode or in direct and relative addressing mode. Then we talked about the special addressing modes, which includes the auto increment, auto decrement, and scaled addressing modes. Then at the end, we discussed the control instruction addressing modes, that is the branch instructions, the procedure call instructions, and the jump instructions. So after this much introduction to the instruction set principles, today our focus will be on the instruction set encoding. The essential elements in instruction set encoding include what type of operations are to be performed. That is, we have to find out or define in some way the operation to be performed, and this is defined with the help of an operation code. This code is defined by using either 4-bit or 6-bit or 8-bit length code, depending upon the type of the architecture. In MIPS architecture, this operation code field is of 6 bits in length. The next important thing in encoding the instruction is to specify the place of the source operands. That is, depending upon the addressing modes, whether the source operand is to be available in any register or it is available along with the instruction in the immediate addressing mode, or it has to be obtained from some memory location by using either the direct addressing mode or indirect addressing modes. Then we have to define where the result is to be placed. The possible location of the result again may be a register of the microprocessor, or it may be some memory location where the result is to be made available. The last but not the least is place to find out the next instruction. Sometimes we can define this along with the instruction code, or presently it is being done automatically by incrementing the program counter. However, now we will talk about in details what are different types of instruction words which are being used to define different or to encode different types of instructions. The instruction words can be classified into different categories depending upon the length of the instruction word. The first and the most simple one is the variable length instruction word. The variable instruction word format is one where we use a fixed length operation code followed by the address specifier and an address field depending upon what is the number of operands and where the result is to be stored. An address specifier specifies the location where a particular operand can be found, and the address field specifies the range in which where the particular address is available. The decision regarding the length of the instruction word depends upon the range of addressing modes and the degree of independence between the operation code and the mode. For example, in the immediate addressing mode, the one of the operand is defined along with the instruction, so this means no memory or register address is needed for this particular case. Similarly, for accumulator type instruction words, one of the location is the accumulator. Therefore, again, no address requirement is there in this particular case. The next second type of addressing mode is the fixed length instruction word format. The fixed length instruction word format is one where first we define the opcode and all instructions have got the same length of the instruction word, where the second, third and higher fields, these are the names or the locations of the operands or where the result is to be stored. Most commonly used fixed length instruction word is the 3-address instruction word, where the first address and the second address, these two addresses are the addresses of the source operands, whereas the third address specifies the destination location. However, both these fixed length instruction word and the variable length instruction word, they have got their own merits and demerits. Therefore, a third type of instruction word format is most common, which is known as the hybrid length instruction word. The hybrid length instruction word format are one where the instruction words may have different length. However, for a particular type of instruction, the length of the instruction word is fixed. For example, if we have to specify the direct addressing mode instructions, then all direct addressing mode instructions will be having a fixed length of instruction word. For example, the first location will be the operation code. The second is the address specifier. This address specifier basically specifies which mode of operations we are going to use, and this defines what will be the number of addresses which will be defined in the following fields, and accordingly what will be the total length of the instruction word. So this mode field basically defines it has got an information regarding the length of the instruction word hidden into it, and it determines whether the instruction word is of 4 bytes or of 6 bytes or of 7 bytes or whatsoever that length may be. And this particular instruction format is being used in the most commonly used microprocessors, that is the Intel ones, where the instruction words may be of 1 byte and it may go up to 17 or 18 bytes in length. So this hybrid length is most popular. However, we will discuss the basic taxonomy of the hybrid length instruction word format in detail. The instruction words of hybrid length, they may be of different types. For example, simplest one is known as the 4-address instruction word format. In the 4-address instruction word format, the first field is used to define the opcode. Then the second field specifies the destination address. The third and the fourth field, they define the two source locations. And the fourth field or the fourth address, which is in fact defined in the fifth field. The fourth address is the address of the next instruction, which is defined as part of the instruction word. The second type of the hybrid length instruction word is one where we use 3 addresses, and this is known as a 3-address instruction. In this case, following the opcode, the first field defines the destination, and the second and the third field define the addresses of the two source operands. So this means that in this particular case, the address of the next instruction is not defined along with the instruction word. Rather, it is assumed that a separate arrangement is being made and the program counter is to be updated automatically to define the address of the next instruction word. The third type of this hybrid length instruction word format is known as 2-address instruction. The 2-address instruction is one where, following the opcode, the first field defines both the destination as well as the source address of the operand 1, and the second address field defines the source address of the operand 2. So this means that the second field, which is following the opcode first field, in general it is second field, it is in the beginning used as, during the fetch time, it is used as the source address, whereas after the execution, this location is used as the destination location. This type of address word format is used in the accumulator-based designs also. The next, which is the fourth one in the series of the hybrid length instruction word format, is 1-address instruction word. The 1-address instruction word is one where, following the opcode, only one field is being defined, and this one field is the field of the source as well as the destination. And in these instruction words, the second operand is assumed to be either available in some of the locations already permanently, or it is not needed with the instruction. For example, if we have to increment the contents of a particular register, then only one address of the register is to be defined with the instruction word for the increment instruction. So the first field will be the opcode, and second field will be identifying the increment operation, that is operation of increment onto one particular operand. After the increment operation, the result is again stored at the same location. Similarly, the last one is known as the 0-address instruction word. The 0-address instruction word is word format is used with the stack-based machines, where the top of the stack always defines the first operand, whereas if this machine has got to a 2-level stack, then the second operand is automatically made available at the second location of the stack, and after the execution of the operation, the result is made available at the top of the stack. So from this point of view, these 5 different methods of addressing, that is the 0 address, 1 address, 2 address, 3 address, and 4 address. All these address formats, they have got their own merits and demerits. Now, with the help of these following two examples, I will show you what is the difference between the execution of a program and writing a program for 0 address up to 4 address based machines. For this purpose, let us have a look onto this example, which is shown here. In order to execute the expression, say f is equal to b plus c whole multiplied by d and minus e. So for this purpose, as you can see from here, by using 0 address format, first of all we have to solve the innermost expression b plus c. So for this purpose, we will first of all place the data onto the stack. So this can be done by using the push instruction, and the push b and push c places the values of the operands b and operand c onto the top of the stack. So once the data is available on the stack, then the instruction used is having only the opcode and no address. For example, as you can see in the third line over here, the word ADD, that is add the two values available at the two topmost locations of the stack. Once this expression has been solved, the result of b plus c is available at the top of the stack. Then, in order to multiply this value with the value d, we have to push the value d onto the stack at the second location. And this is done by the third push instruction, which is followed by 0 address instruction word MUL, which is used for multiply operation. Now, as a result of this operation, the first part of the expression, that is b plus c, has been multiplied with d, and the result is now available at the top of the stack. Now, in order to subtract the value of e from this result, we have to push the value of e onto the second position on the stack and then issue the instruction SUB, which stands for subtract. The result of the whole expression is now available at the top of the stack, which can be placed at a location f by using the pop f instruction. So this way you can see that the 0 address instruction word format has got, it needs 8 instructions in total. Whereas if the same expression is to be solved by or is to be executed by 1 address instruction word format, then one of the operand in these type of instruction words has to be first of all made available onto the accumulator before issuing the instruction. So for this purpose, the first instruction, that is LDA, which stands for load accumulator, and we have to load the value of the operand B onto the accumulator before issuing the instruction add. So the second instruction, which is ADD, which stands for add, followed by on the location of the operand, which is equal to C. So this instruction is basically executed on the principle of 1 address instruction word, where one of the operand is available in the accumulator, second operand is defined along with the instruction, and after the execution of the instruction, the result is placed onto the accumulator. So the result of B plus C is now available onto the accumulator. Therefore, the next operation, which is multiplication of B plus C by D, is done directly by issuing the instruction MUL, which stands for multiply, and followed by the address of the operand, which is D. So as a result of the execution of this instruction, the first part of the expression is completely executed, which is b plus c have been multiplied by d. Now this result is again available onto the accumulator, and we have to subtract the value e from this. Therefore, the next instruction again is one address instruction sub followed by the address of the operand e. So this completes the execution of the complete expression, and as this result is now available onto the accumulator, it is to be transferred into the memory at a location C, which is done with the help of a store accumulator instruction, which is written here as STA. STA followed by F again is a one address instruction, and it is used to execute the expression. This type of instruction, one address instruction word format, it requires, as you can see, only 5 instructions in order to execute the same expression. Whereas, now let us consider the two address instruction word format. In the two address instruction word format, as I defined earlier, first address is in the beginning used as the source address, and at a later stage it is used as the destination. So for this purpose, basically the load F, one location is F, and it is to be loaded by the value of the operand B. Now this operand B is available at the address F. The second instruction, which is add F comma C, it stands for to add the value of C into the contents available at the address F. Now the result is available at F, and therefore the next instruction MUL, which stands for multiply F comma D, stands for multiply the contents of F by D, and whatsoever is the result, that is made available at the location F. And the last instruction over here is subtract F comma E, means whatsoever is available in F, from this subtract E and make the result available at the F, which is the actual desired location. This is why no store instruction is required in this case. And this shows that we can execute this whole expression by using only 4 instructions. The 3 address word format, we need only 3 instructions in order to execute this expression. As you can see from here, the first instruction is the add instruction followed by the 3 addresses. In this case, F is the destination address, B and C are the 2 source operands. So the first add instruction therefore adds the contents of B and C and stores the result in F. Whereas the next instruction, which is multiply FFD, means that we want to multiply the contents of F with the contents of D, and whatsoever is the result, that will be stored at location F. Whereas this means that first part of the expression is now complete, and from this value we have to subtract the value of E, and this subtraction can be done with the help of the last instruction, which is subtract F comma E, means subtract the contents of value of E from the value available F and make the result available at F. And as you can see that it requires only 3 instructions in order to execute this expression. So this shows the difference between different types of instructions. And now let us see another example. As I told you in the beginning, that we can solve this with the help of different type of instruction words. And in this case, now in this second example, you can see we want to execute relatively complex instruction expression, which is Z is equal to 4 multiplied by A plus B. From this whole expression, now we want to subtract 16 multiplied by C plus 58. So it requires basically the execution of this whole program in two parts so that we can get the final required result. For this purpose, you can see from here the solution for all these four type of instruction word formats which we have talked about earlier also. And in order, I think you can very well understand from this how these programs have been written for 0 address, 1 address, 2 address, and 3 address. Once again, you can see from here that in case of 0 address arrangement, we have solved the last second sub-expression, which is C plus 58. We have solved this first, and we have solved the second part sub-expression, that is A plus B afterward. The reason for this is that the subtract instruction, which is given as the second last instruction over here, it has to subtract the contents of the second location from the top of the stack. And as we want to make the value of C plus 58 at the upper position and A plus B multiplied by 4 at the lower position, this is why we have decided to solve the second sub-expression first and the first expression, sub-expression afterward. However, as an exercise, you can try solving this problem in an opposite sequence, and you can see the difference. You may need some additional pop operations, and this will increase the length of the program. Similarly, you can see that in the one address arrangement, as you can see, we have in fact changed the order in order to reduce the result. Again, in this case, what we are doing is we are solving the second sub-expression first and the first sub-expression afterward. And this, in fact, simplifies the solution of the program. So this type of arrangement is not needed in case of two address instruction word format. Again, the reason for this is that in the two address format, we can control this, the sequence in which last subtract operation is to be performed, how the operands are to be defined. That is, whether we have to say SUB, Y comma S, or S comma Y. It depends upon this, in which sequence we have written the previous parts of the whole program. Similarly, you can see that the three address arrangement is further much more flexible as compared to even two address instruction word format. However, both these methods, they have got their own merits and demerits. We can compare the instruction formats for 0 address to 4 address instruction word formats by considering the code size and the memory, number of memory cycles which are required for the accessing of these instruction words. So for this purpose, let us consider a case where we can assume that the instruction byte is, instruction opcode is of 1 byte. The address of the memory is such that its address can be written as a 24-bit long address, and the size of the data bus is of 8 bits. For this purpose, let us consider this slide and let us see how we can compare or find out the total size of the instruction word. As you can see from here, we can in fact see that we need, as the size of the memory space can be addressed by 24 bits, each address requires 3 bytes. Therefore, for a 4 address instruction word, 12 bytes are required for addressing and 1 byte is required for opcode. Therefore, 13 bytes are required for instruction fetch and 6 bytes for source operand fetch and 3 bytes for storing the destination operand Thus, it gives us the total of 22 bytes. Similarly, for 3 address arrangement, as you can see from here, the code size is now 10 bytes, whereas the number of bytes to access the memory are, that is 10 bytes for instruction fetch, 6 bytes for the source operands, and 3 bytes for storing the destination operand. This gives us in total 19 bytes. Whereas for 2 address instruction words, the code size is 7 byte, whereas the number of bytes accessed from the memory is 7 for the instruction fetch, 6 for the source operand, and 3 bytes for storing the destination operand, and this gives us total 16 bytes. Whereas for 1 address instruction word, the code size is 4 bytes, 3 for the address and 1 for the opcode, whereas the number of bytes accessed from the memory are 4 bytes of instruction, 3 bytes of the source operand, 0 byte for storing the destination in this particular case. Therefore, total is 7 byte. Whereas for 0 address instruction word, code size is 1 byte. Therefore, number of accesses from the memory is 1 byte for the instruction fetch, 6 byte for the source operand, and 3 byte for storing the destination. Thus, it gives us total 10 bytes. So, now you can see that in this table shows that the 1 address instruction word has got minimum number of memory bytes, and no doubt the code size is 4, whereas in case of 4 address instruction word, the number of memory bytes required is equal to 22. So this shows that 1 address instruction has got, it requires minimum number of memory accesses, whereas for the 4 address, it requires maximum instruction word. So with this much discussion about the 4 different types of addressing formats, we will extend this concept further, and we will see that how the instruction words are being designed for a specific type of system, which is we will be considered for this purpose the RISC and the MIPS 64 instruction set architecture. And for this we will see what are how this instruction word can be designed. So for this purpose we can see from this slide that the RISC and the MIPS is a fixed length 64-bit load store type of architecture, and it contains 32 general purpose registers. Each register is of 32 bits, whereas it supports 3 addresses: register arithmetic instructions, displacement type instructions, and address offset of 12 to 16 bits. It also supports immediate data types of 8 bits, 16 bits, 32 bit, and 64 bits. The data size is of these different values. So it also follows 64-bit IEEE floating point word format. It also supports the instructions such as data transfer instructions, which include the load store instruction, register move instruction. It also supports simple arithmetic instructions like add, subtract, logical instructions like shift logical or simple shift, whereas it also supports the compare instruction and branch instruction. The compare instructions include equal, not equal, less than, and based on their results, it can be branch, and this branch can be PC relative or jump or call to a procedure and return from the procedure. Furthermore, the MIPS architecture is designed for pipeline efficiency. However, let us talk about the MIPS instruction word format. For this purpose, we can say that mixed instruction word is designed such that it has got three different types of formats known as the register type of format, are normally written as R type format. Second is the immediate address format, and that is usually written as I type format. And the third one is the jump format, which is usually written as J format. So let us consider first of all this R type format. For this purpose, have a look onto this. You can see that the instruction word over here has been divided into 1, 2, 3, total 6 fields, where the first field is the opcode field, which is of 6 bits in length. The following this are 2 fields, which is RS and RT, that is the source register and temporary registers, which are usually used to keep the addresses of the two, or the contents of two source operands. So each of these register address field is of 5 bits, because as I told you in the beginning that this MIPS architecture has got in total 32 registers. Any one of these 32 registers can be addressed by using a 5-bit address code. Similarly, the third address field and the fourth field in the normal sequence, that is, the first one is the opcode, second and third are RS and RT, and the fourth one is RD, which is the destination register. It is also of 5 bits in length, whereas the next field, which is written over here as SHT, it is SHT basically stands for the shift amount, and this field is used only with the shift instructions to specify how many bits are to be shifted from 1 up to 32-bit shift. 32-bit shift, which means it again requires 5-bit code for this purpose. The last field over here is known as the function field. Function field is used only when the opcode field contains a value equal to 0, 0, and the opcode field contains a value equal to 0, 0 in case of register type or R type instruction word. So the function over here is, as you can see, written in the register transfer language over here, that is RD gets an information from RS function RT. So when the function RS function is applied onto the contents of the register RS and RT, the result is made available in the destination register RD. So you can see it with the help of this next example shown over here. This is an example of arithmetic instruction and shift instruction. First, let us see how the instruction word appears for arithmetic instruction. In case of arithmetic instruction, as I mentioned earlier, the opcode field for register type instruction always contains a value equal to 0, 0. Whereas the function is defined in the bits 0 to 5, this 6-bit field function defines what type of the instruction word is this. So in this particular case, the assembly language code DADD, it stands for the add a word long data. And as we have already mentioned earlier, that word in the case of MIPS architecture is of 32 bits. So all these registers are also of 32 bits. Therefore, we can see the meanings of this instruction are that add the contents of register R3 to the contents of register R2, which are defined in the field from bit 21 to 25 and bit 16 to 20 over here. And the third field over here is for the destination location, which is R1. And in register transfer language, you can see from the first line that it is the contents of the sum of register R2 and register R3 is transferred to register R1. Please note over here difference in the sequence when it is an instruction is written in assembly language and when it is written in the instruction word over here. As you can see from here, the sequence is while moving from left to right. In case of the assembly language program, first we write the destination address and then we write the source operand addresses. Whereas in the machine code or in the instruction word format, moving again from left to right, first the RS and RT, that is the two source operand locations, are defined, and the third register over here is the destination register. So these two sequences are opposite to each other. However, as the next part over here, as you can see from this slide, is the shift instruction. The shift instruction is one where only one of the operand is needed, because the shift instruction says, as in this case, DSLL stands for shift left logical, which means whatsoever are the contents of the register R2, they are to be shifted by the amount defined in the amount field, which is the field ranging from bit 6 to bit 10, and this is in this example equal to 30, which means that we want to shift the contents of the register R2 by 30 bits and to the left and place the result in register R1, and it can be written in register transfer language as register R2 shifted to the left. The arrow sign over here towards the left with its arrow direction towards the left indicates that it is a shift left operation by 30, and the value is after shift operation transferred into register R1, which is the destination register, which is defined in the instruction word by bit 16 and 20, and it is written in the first location on the left hand side in case of assembly language. Now let us consider the second type of instruction word, which is known as the immediate type of instruction word format. The immediate type of instruction word is one which is divided into 4 fields. As you can see it from here, these 4 fields, again reading them from left to right, are the fields for the operation code, field for RS, and field for RT, and then a 16-bit field to define a 16-bit immediate value. Here you can see, note down one difference as compared to the register type instruction word. The difference over here is in the field RT. The field RT over here in this instruction, it is used for the destination location, instead of using this for a temporary register, as in the case of second field, a second address field in the case of register type instruction was RT. But this location is no doubt for RT, but actually it is the destination register in case of certain instructions. Again, looking into this, the same instruction word format can be used for immediate data type as well as for load and store instruction. However, the 16-bit field used over here is used when it is to be used for as an immediate data. The immediate data is obtained by using this 16-bit value and passing it through a sign extender, and this sign extender extends the sign bit to convert this value into a 32-bit data. Whereas in case of load and store instruction, this immediate field, it gives 16-bit address. Again, this 16-bit address is used in different ways for the manipulation of the address of the operand. in case of load and the store instruction. Again, the load instruction is one where we want to read some value from the memory and place it into the register. So this means the destination is a register and source is a memory location. So the memory location means we need a 32-bit address of the memory where from the data or the operand is to be read and it is to be placed into the destination location. So for this purpose again, this 16-bit address is either used in the relative addressing mode and it is added into the contents of the register RS, and then the value is read from that particular location and it is loaded into the destination register. Whereas in the case of store instruction, the significance of RT is different, because the store instruction actually means that we want to read the value from a register and store it into the memory. So in this case, the address will be the destination address. So the next type of instruction word which we want to discuss now is the J-type instruction word. As you can see now from here is this J-type instruction word or jump instruction word is again instruction word which has got 4 fields, and this is identical to the immediate instruction word format. However, over here the significance of this immediate value in this case is that the immediate value gives us the value of the location where it is to jump if the condition is met, and the condition is basically considered or tested by using different modes of operations. For example, as you can see over here, it can be used to compare and or test. For example, in the case of the instruction branch equal Z means BEQZ means branch if equal to 0. So if equal or 0, then it has to branch, and in case it is not equal 0, then it does not branch. So the condition tests the register for 0 or non-zero. Similarly, the BNE, that is the condition is branch if not equal. That is, the two registers are compared, that is the register RS and RT are compared, and if these two registers are equal, then it is the branch is, that is the contents of the program counter are changed to branch to a new location which is defined by 16 bits, and these 16 bits are used to replace the lowest 16 bits in the case of the program counter. So again, it is used through the sign extender and it is converted into this format. We will talk about this in details when we will discuss the design of the data path and how this instruction fetch circuit is being used and this data is updated. The next, you can see that the jump instruction word has got 2 fields only. The first field is the opcode, which is again a 5-bit field, and the remaining 26 bits are the target address. However, these 26 bits are used by shifting 2 bits to the left for aligning the boundary of a 4-bit instruction word. The total 28-bit address is the new address which is transferred into the program counter. However, the jump instructions are of 2 types, that is simple jump and link. Jump and link is usually used in case of call for the procedure, and it contains the address, return address, which is the contents of the program counter, which are which are stored into the register, and this register then later on gives a register R31, basically contains the return address, and when a program executes the return address, it is available in register R31 and it is used for this purpose. Now, at this stage, we will stop our discussion regarding the instruction encoding and instruction word designs, and I will give you a brief summary of what we have discussed today and what we will be doing next time. Today we have started our discussion with instruction encoding, where we talked about the essential elements of computer instructions, that is, what are the types of operand, what are the places and places of the source operand and the destination. Then we talked about the instruction word length, hybrid type instruction taxonomy like 0 address, 1 address, 2 address, 3 address, and 4 address formats. And then we discussed, I gave you the comparison of hybrid type instruction word format in different cases. Then we discussed the instruction word format for a RISC or a MIPS based MIPS architecture, and wherein we discussed what are the operand sizes, how different types of instruction words are being written, and how these instruction words are formatted. So with this, we close our discussion for today, and next time, inshallah, we will continue with our discussion on the instruction word format and instruction set architecture in a concluding form. Till then, Allah Hafiz.